Welcome to qnawire.
In this exercise, we have this wave packet, phi of x, that is equal to the integral from 0 to infinity of b of k times the cosine of kx dk. And b of k is defined as the exponential of minus alpha k squared, where alpha is a positive real value. In question A, we define kh, which is the value of k for which bk decreases to half its initial value. Now notice that its initial value, when k is equal to 0, is equal to 1. So b of k equals 0 is 1. And we define the width of b, so omega k, actually wk, as kh. And in question A, we have to find wk as a function of alpha. So notice that b of kh is equal to half the initial value, so it's 1/2. So, and this is e to the minus alpha times kh squared. Okay, so if I take the logarithm, the natural logarithm on both sides, we get that minus ln of 2 is equal to minus alpha kh squared. So kh is equal to L, actually, the alpha should be squared here, I'm sorry, according to the exercise. So kh is equal to the square root of ln of 2 divided by alpha. Okay, so this is the value of kh. So this means that wk is equal to the square root of the logarithm of 2 divided by alpha. This is the answer to question A. Then in question B, we have to use integral tables in order to find the explicit value for the wave function psi of x. So we have the integral from 0 to infinity of e to the minus alpha squared k squared times the cosine of kx dk. And if we just look this on an integral table, as the exercise asks us to, this is the square root of pi times e to the minus x squared over 4a divided by 2a. Okay, so this is the value of psi of x. And the exercise also asks us to calculate what is its maximum value, for which value of x does psi has the maximum value. So notice that the exponential of minus x squared over 4i is smaller or equal to 1, and it's equal to 1 when x is equal to 0. So psi of x equal to 0 is the square root of pi divided by 2a, and this is the maximum value of the wave function for x equals 0. Then in question C, we define the width of the wave function wx as the value of x for which the wave function decreases by half. So we have xh. So notice that this happens when the exponential, which for x equals 0 is 1, becomes, so we have the exponential of x squared, xh squared divided by 2a becomes, well, by 4a squared, I'm sorry, becomes 1/2. So again, if we take the logarithm on both sides, we get minus xh squared divided by 4a squared is equal to minus ln of 2. This means that xh is equal to 2a times the logarithm of 2. So wx, the width, is 2a times the square root of the logarithm of 2. Then finally in question D, we have the information that the width of the function b in the momentum is equal to h divided by 2 pi times hk. I'm sorry, that times wk. That is the result we found in question 1. And given this, we have to find the multiplication wp times wx. So notice that this is h divided by 2 pi times wk times wx. Now wk is equal to 1 over alpha times L, the natural logarithm of 2, and actually up here, instead of being a, this all should have been alpha. I'm so sorry for that. Okay. And we have to multiply this by wx, and wx is equal to 2 alpha times the square root of the logarithm of 2. So notice that the alphas cancel out, and we get that wp times wx is equal to h divided by 2 pi times the natural logarithm of 2. Okay, notice that this looks a little like Heisenberg's uncertainty principle for minimum uncertainty when delta p times delta x is equal to, or approximately equal to, h divided by 4 pi.